Great, thanks. Thank you for that, and thanks for Carol for inviting me again. I was at the first workshop, so it's great to be able to do the follow-up today. And there's a lot happening in this space, and I'll give you some insight into that in a minute. So I'm from the National Oceanography Centre. I'm Chief Scientist of the Marine Autonomous and Robotic Systems Fleet that's dominantly hosted at the National Oceanography Centre. And I'm going to be talking about how we use marine robotic vehicles for marine environmental research. I'm not going to talk specifically about defence applications, but I think some of the crossovers relevant today will be self-evident as I go through the talk. First point, RRS Discovery is one of our Royal Research ships, £75 million worth of research vessel, costs upwards of £20,000 a day to run. That whole fleet of marine robotic vehicles is 1/10 of the cost of that research vessel. That's just the first point. One of the consequences of that discrepancy in cost of running vessels and buying the capital around research vessels is that BIS, what's now BEIS, and NERC, our parent research council, has invested quite heavily in marine autonomy, both to replace but also augment what we can do with vessel-based marine observation. So really the long-term goal for us is to get more data, better quality data at lower cost to support scientific research. So as a consequence, we now operate more than 40 marine autonomous systems as part of the Maz fleet. Most of that's based at NOC in Southampton. Some of it's based at our partner operations, the Scottish Association for Marine Science operating out of Oban, and the British Antarctic Survey, who have an operating base down in Antarctica. As well as the platforms that I'm going to give you some examples of in a minute, we also, in Southampton and more widely within the NERC community, have a lot of capacity to develop innovative sensors to go on these platforms to measure new things in the ocean environment. And increasingly, to pull platforms and sensors forward, we're working with small businesses, and we have a new innovation centre at the Southampton site where we're bringing together companies that are building software solutions, new platforms, new sensors to work with our engineers and scientists to drive this area forward. So what do we talk about in terms of marine robotic platforms? Traditionally, North Sea oil and gas was one of the big drivers of tethered systems like remotely operated vehicles that can have high power transmitted down to them via a tethered cable, and you can get live video and lots of data streaming back to your parent vessel or platform. A true autonomous system, something like an autonomous underwater vehicle, a propeller-driven vehicle, operates on a straight trajectory through the water column like a submarine. Typically, these have been fairly high-power, short-range vehicles that might have an endurance of 2 or 3 days maximum, but they can do everything from seabed mapping to a range of physical and biological measurements. And we've got a couple of in-house vehicles, Sub 3 and Sub 6000, the latter that's depth-rated to 6,000 metres water depth, that we've been using for getting on for a couple of decades now, and there's other commercial variants of that. I'll talk a bit about Sub long range in a minute, which is a longer endurance AUV, a novel development. Another platform that's been kicking around for a long time, Submarine Gliders. US Defence is the biggest purchaser of submarine gliders. There's 2 main suppliers in play at the moment, Teledyne Webb and Kongsberg. We've got about 30 of them. A relatively low-cost platform compared to a big AUV. They have a buoyancy engine, so they oscillate through the water column like this and surface every few yows to transmit data and get commands back, and they move relatively slowly, but they can go out for many weeks at a time collecting data. And then most recently, we've seen the emergence of a number of different types of unmanned surface vehicle. Most of you will probably be familiar with the Liquid Robotics Wave Glider. It's done some high-profile missions, many hundreds of kilometres in the right sort of conditions, collecting data at the air-sea interface. So this gives us the ability to collect data on weather, phenomena that are happening above the sea surface. But there's others. We've got 2 in the fleet, the Sea Enduro and the Autonaut, that are new USVs that have come into production in the last couple of years, and there's almost a new type of USV coming out on a monthly basis. It's a very immature area, this one, and some of the different designs have different utilities, and that's all going to come out in the wash in the coming months and years. So ROV is a very mature technology. AUV is pretty mature. If you put an AUV in the water, you've got high confidence it's going to do what you want it to do and it will come back. Gliders maturing. I think we're getting pretty confident now of putting gliders in the water and getting them back. Unmanned surface vehicles is a less mature technology, but in certain areas like the oil and gas sector, in some of the more warm parts of the world where there's a predictable wave climate, they're being used for commercial purposes as well. To run all of those platforms that we have in the fleet, let's say it's just over 40 platforms, we've got a staff of about 30. And one of the key things we talked earlier about training and experience, you need experienced pilots to run these vehicles. And that's why you can't do away with, because we build some of our own vehicles in-house, but also we pilot our own vehicles, we need a reasonable sized team of people behind it. I'd also add that on the right here, there's a gradual evolution through time as I've gone through these different platforms between increasing endurance, so platforms that can go from just doing a few hours to a couple of days to being able to operate for weeks to months at a time in the ocean. Increasing flexibility, so platforms that don't require a ship to get in and out of the water, but could be deployed from a rib by a couple of guys or from a slipway or a beach very rapidly and very easily. We're looking at increasing interoperability, so different types of vehicles working together. So you might have an AUV working at depth for weeks at a time. You don't want to bring it to the surface, so you have an unmanned surface vehicle with an acoustic communication link between the two, so you can get data coming from your deep AUV via an acoustic link to your surface vehicle and back to your operating base via satellite. We're also looking at other combinations, so we're looking at unmanned surface vehicles that could maybe release tens of very small AUVs for rapid response, or we're seeing submarine gliders that could be thrown out of a plane or a helicopter into the water and could then operate, or other vehicles that can fly into the water as a quadcopter and then evolve and do some AUV type work as well. So we're seeing hybrid vehicles coming online all the time. We operate relatively dumb vehicles at NOC deliberately. We keep the vehicles simple and we have hopefully reasonably intelligent pilots and scientists behind them. But there's a general trend towards having more intelligence in the vehicles, so that if an AUV is on mission at 6,000 metres water depth and it finds something interesting, rather than just carrying on with its pre-programmed mission, it will recognise it's found something interesting and alter its search pattern and home in on that feature of interest. Or it may be that there's onboard processing to sift out all the huge amounts of data that the platform is generating and only send back the stuff that it thinks will be of interest, which A, brings down cost, and it reduces the burden on the interpreter back at base. Generally, the platforms that we're using are getting lower in cost. A big AUV with all the sensors on it, you won't get much change from £500,000 up to £1 million. Some of the unmanned surface vehicles are coming in sort of tens of thousands of pounds. So there's a big range of cost. And then very small miniaturized platforms that have limited capability but could be mass produced would be even cheaper. One consequence of long endurance is you have to bring speed down, inevitably. So there are not many small research-capable platforms that can go at high speed for long periods. On the research side, we've brought the speed down. So most of these platforms, AUVs, gliders, some of the USVs, they don't go much faster than walking or running pace. So they're not going chasing across the ocean at 10 knots. They're relatively slow, but they're going out for long periods. So what parts of the ocean can we access? Well, we've been going under ice for a couple of decades now. We pioneered under ice work with the first part of the family of autosubs. We can routinely go in many tens of kilometres under the ice and do things like under ice mapping, both of the seabed and the underside of the ice shelf. We can image things like krill to work out what's the krill biomass under the ice compared to open water, etc., etc. So we've been going under ice for a while, and there's not many other ways in which you can get under ice except with an AUV or a submarine. So obviously you're not able to get under there with a ship. We can get to the deepest parts of the ocean. I mentioned Autosub 6000 can get down to 6 kilometres water depth. We've discovered, mapped, sniffed the world's deepest hydrothermal vents using that platform. We've mapped the seabed, we've gone in with chemical sniffers, detected an anomaly, and that enables us to go in with an ROV and collect live video that can be beamed back into people's living rooms on the 6 o'clock news. So you can be watching the news and there's a live image of a black smoker chimney at 6,000 metres water depth. So the technology is enabling us to get into parts of the deep ocean and communicate that to the public in ways that we've never been able to do before. Around the UK, particularly as you come off the continental shelf, this is the northern part of the Bay of Biscay, Whittard Canyon. It's just at the very edge of English real estate. It's very complex terrain. Canyons are very difficult areas to work. You imagine trying to take many types of terrestrial vehicle in and around the Grand Canyon, it's nearly impossible. Likewise, it's quite a challenging environment to work for marine robotics, potentially good hiding place for biology and other things. with ship-based systems that only look down, it's very challenging to get good data from these three-dimensional environments. If you look at the scale of this map, this is 200 kilometres. This Whittard Canyon system is a couple of hundred kilometres across. It's a big canyon. So how do you go about imaging it? Well, with a ship, you could produce a 3D map like this, but your resolution of your pixels might only be a few tens of metres. So you're not getting very good quality resolution using ship-based mapping at water depths of up to 4,000 metres. So to really get into an area like the white rectangle, you need an AUV. And we've pioneered a method where we can actually not just downward map with an AUV, but we can sideways map the walls of canyons and even underneath overhangs by flying the AUV within the canyon. It's quite challenging and it's quite high risk, a bit like flying an aerial drone down the middle of the Grand Canyon. But what you get is a 3D perspective at an order of magnitude better spatial resolution than your ship-based mapping, and these are the pings from the ship-based map here. So you're really getting a much better density of data by flying the AUV within the canyon. And then if you have a feature of interest like a rocky wall, which in this case is a useful habitat for things like cold water corals, you can go in with an ROV and do sideways mapping at an order of magnitude higher resolution, again getting down to decimetre scale, maybe about this sort of resolution. And you can even image overhangs and areas where you've got lots of interesting biology, and you can start getting down to millimetre scale resolution with the ROV. So this is how we would approach difficult terrains like canyons. We have this nested mapping getting finer and finer detail. And then as well as that, you can simultaneously fly a submarine glider in there, so you get the oceanography as well, so you're getting geology, biology, oceanography simultaneously within a big canyon system. One of the other developments I mentioned, daughter sub long range. So what we aspired to was an AUV, a propeller-driven AUV that could go for weeks and months at a time, depth rated to 6,000 metres and with a range of many hundreds, if not thousands of kilometres. So by bringing the speed down, improving the battery performance, miniaturising the sensors and increasing their power efficiency, we've been able to do that. It's not going to do high-power seabed mapping with big multi-beams and geophysical instruments, but it will collect a wide range of oceanographic and biological data. And what we can do with something like Ord sub long range is occupy, for instance, a choke point, an ocean choke point, in this case the Drake Passage, for many weeks to months at a time, doing repeat transects. We have an aspiration within 5 years to cross the North Pole under the ice, using train-based navigation, for instance, to get from one side of the Arctic Ocean to the other. And we also plan to use it for things like self-deploying moorings. So you would launch it from, say, Penzance Harbour, and it would trundle out to an area in the deep ocean, and it might do some up and down vertical profiles of the water column for a science study, and then it might hibernate, and then it might wake up 3 months later in a different season and repeat the process, and then hibernate on the seabed and repeat. So there's a whole range of different utilities in science and other areas where having a long-range AUV opens up new capability. A lot of these assets we can control from operations room at Southampton, so we can have assets anywhere in the world. And a bit like Tim Peake, recently he was in space and he was able to control effectively an inverse Mars rover that was on Earth from up in the space station, as shown here. We can control any of our fleet, and on an iPhone I can see where any of my gliders or unmanned surface vehicles are at any time, with a whole range of other data layers to inform any part of the day, wherever I am, what's going on during the mission. And that's really important, because then that enables me to communicate with the pilots and say, right guys, actually there's an interesting feature that's cropping up over here, or I don't like the look of this storm that's coming in, let's pull our USVs out and get them a few kilometres south. So Rolls-Royce also have a concept for commercial shipping with unmanned ships, where you have a central operations room and you're controlling a whole load of unmanned ships for things like commercial freight applications. One of the things we've tried to do with marine autonomous systems, and it's been a challenging area around drones in the air, is making sure we portray a positive image of the sector. One of the things we're trying to do is support UK business in growing in certain areas of developing the platforms, the sensors and the C2. And so we've worked very hard to have good relationships with the media to show the positive benefits around marine environmental research and getting better, high quality data to improve the way in which we manage our marine environment. And that's been a big part of what we've done with a series of missions called Mesmo, which are really demonstrator missions that have been happening on an annual basis for the last 3 years now, where we get a whole load of partners together, put a load of platforms and sensors in the water, give them some challenging tasks and see what happens, and literally learn from our mistakes. a lot of what we're finding is basic seamanship when you're operating these things is still really, really important. Even though they're robotic vehicles, understanding how they respond to different aspects of the marine environment is key. So during one of the first Mesmos, we just used submarine gliders and we loaded them with as many sensors as we could to monitor all aspects of the marine environment and the ecosystem, from plankton through to fish and marine mammals. So we had both active and passive acoustic devices on those gliders and learnt a lot from doing that. So for instance, we can image fish shoals. So this image on the top left, a glider going down, you can see the seabed at the bottom and these fish marks. Very comparable signal to using a fisheries echo sounder on a vessel like the CFAS Endeavour, which is the image on the right. So we can use fisheries acoustics on a submarine glider. And we can use passive acoustic monitors to pick up echolocating dolphins and porpoises, etc. So we know that we can do that. What submarine gliders are particularly useful for is collecting many thousands of profiles that can be compressed into a 2D section over periods of weeks. So here's some data from this spring off southwest UK. This is about a 3-week period, water depths from 0 to about 100 metres on here, and this is many hundreds of dives of the glider as it was moving towards shallow water on the Isles of Scilly. And in this area, it was in stratified water, so this was late spring. Thermal heating meant that we had a good warm surface layer, a good thermocline. The glider was able to image that, and every few profiles it would come up to the surface and send live data, so we knew exactly where the thermocline was, what the temperature gradient was across it, etc., etc. And then as the glider progressed into more mixed waters near to the Isles of Scilly, it crossed a tidal mixing front, which is a vertical boundary. Now these boundaries are important for biology. They're also important because they act as acoustic interfaces in the ocean, and there's obvious applications there in defence. So gliders can image these in real time. It's very hard to replicate this using satellites or models to this degree of detail, and they can send the data back in near real time to an operations room. Unmanned surface vehicles are best viewed really as a sort of marine version of the Mars rover. They're going into a hostile environment, we're loading them with lots of different types of sensors, and we're communicating with them pretty much continuously via satellite. These are 2 new vehicles that NOC has been involved in developing with SMEs as part of a small business research initiative. 2 companies based in southern England have built the Autonomy and the Sea Enduro, and together with the Wave Glider, they each have different strengths and weaknesses and different utilities. They can carry a range of sensors, everything from cameras and video at the surface to towed acoustic arrays, weather stations, etc., etc. And they can also take water samples. And the Sea Enduro has the capability of having a little winch, so it could drop a CTD or a sonar buoy or something from the surface and go profiling in the water column. The imagery that we've been collecting just with off-the-shelf GoPro cameras has been pretty good. Here's the Autonaut with a towed array, 25-metre-long towed array behind it, and an image of an adult northern gannet off the Isles of Scilly. This vehicle on its maiden voyage did 450 kilometres in 12 days and went through 2 significant Atlantic storms. We had winds 70 miles an hour, waves up to 7 metres high, got a bit battered, but it survived, and the towed array came back all in one piece, which was pretty impressive for its first voyage. And sometimes they can take images of interesting features, such as this Navy vessel that didn't know it was being photographed at the time. What we've developed with one of the more recent Mesmo missions this spring was the ability to send back real-time images, in this case from the Sea Enduro vehicle. This is a Northern Former. It's good enough detail. You can see it's in wing molt. This was in late spring. This is again off southwest UK. We were having a live image from the vehicle coming in every minute from the forward-facing camera. Effectively, if you had a bit more money and a bit more time to design it, you could have a 360 field of view with images coming in as often as you wanted back into the control room. And then what we could do is, if we wanted a high-resolution version of that image, we could request that. The low-res versions were about 2p per image, and the high-res versions via satellite about £1. So we're literally having eyes in the ocean as well as the acoustic devices having the ears on the vehicles as well. And then with the mission control, we can see where the vehicles are. This is the Isles of Scilly here. And we can overlay various data layers like the weather. In this case, it's a tidal prediction model, so we can see how the tide might be affecting the vehicles in the next few hours. It could be satellite imagery of ocean colour or temperature. It could be AIS shipping information. So there's a number of data layers you can just switch on and off. And again, I can do this on an iPhone wherever I am and whatever I'm doing. So I can keep control of the mission and keep abreast of what's happening almost in real time. The next Mesmo actually starts in a few days' time, Mesmo 3, which is going to be our contribution to exercise Unmanned Warrior, which is the unmanned component of Joint Warrior 16-2 off northwest UK this autumn. And the idea of Unmanned Warrior, which was basically sponsored by the First Sea Lord, was to demonstrate how unmanned capability can enhance and in some places potentially replace manned capability for the benefit of the armed forces. So our contribution to this is going to be around the geospatial intelligence theme. NOC is coordinating an activity under the Mesmo 3 banner where we're going to have 11 different vehicles going in, so up to 8 submarine gliders and 3 wave gliders are going to be going in. We're coordinating that fleet. We think it's the biggest mass deployment of marine robotic vehicles undertaken so far in the UK, and this is just contributing to one theme. There's also mine countermeasures, ASW, ISTAR, etc. So there's going to be a lot of unmanned systems all doing different things as part of exercise Unmanned Warrior. But with our fleet, we're working in partnership with Royal Navy and DSTL and others to look at what the marine environmental data is that we can collect with these platforms and how does it improve upon traditional data that the Navy would use, such as models and satellite imagery and weather forecasts, etc. So there's a whole range. There's about 20 partners that are going to be involved in that. I'm sure you'll see some of the stuff around it coming out in the media in due course. And then finally, what we're trying to do is, as well as viewing these platforms just as a way of collecting data in isolation, we already have a pretty good infrastructure in the marine environment around the UK. We do have ships, we have platforms, we have buoys, we have satellites, we have models, lots of different ways of gathering information, and these autonomous platforms are just a new way of gathering information, and we need to not throw all those old methods out. So we need to find ways of getting the whole network of different types of platforms, both mobile and fixed, remote sensing and in-situ observation working together. And we have a new program within NERC in partnership with DEFRA, DSTL and others. It's about $3.5 million to look at how we develop a next generation observing network for UK shelf seas. So that has defence application, environment applications for DEFRA, research applications for long-term monitoring of our oceans as well. So this is where we're moving next, is how do we get all these different things working together and how do we handle all the massive amounts of data that are coming off them. I'm slightly worried that on Monday morning I'm going to be going into the operations room in NOC and there's going to be 11 vehicles beaming back from multiple sensors data at me simultaneously, and trying to make sense of it all is going to be fun. So that's me. I just want to flag that we host an annual Marine Autonomy and Technology Showcase at NOC. The one this year is in November. There's the dates. The front end of the week is more geared towards working with industry, both people that are producing new platforms, sensors and softwares, but also user industries like oil and gas and renewables. And then the latter stages of the week, we have a science showcase. As many of the things I've shown today will be discussed in more detail. And we finish up with a Mesmo workshop where some of the lessons we've learned, and particularly mistakes and failures that we've had during the Mesmo missions, we share that so that as a community we can all move forward and hopefully not make those same mistakes again. Okay.